Okay, so in this example, we have a simple series circuit, 3 resistors in series, value of each one is given, and a source over here represented by a battery symbol with a value of 32 volts. We are asked to calculate the total current and the voltage drop across each resistor. And so, in order for us to do that, go back to your rules for series circuits and have a look at those. And so, before we can apply Ohm's law to any individual resistor, we have to have 2 pieces of information about it. And because they're in series, the 32 volts does not appear across any of the individual resistances. The 32 volts appears across RT. So before we can do a calculation, we should find RT. Now, this little box right here is called a VIR chart. And if you sketch that, for the circuit, you can put your information in there. And it kind of helps you keep the information you have calculated, keep it straight. There's a line for each resistor, 1, 2, and 3, with the given information in there. And of course, the T represents totals, so a line for totals. So far you have the total voltage and you have the resistance of each individual resistor. And so until you have 2 pieces of information about the circuit or about any individual resistor, you can't use Ohm's law. So we'll start off then by calculating RT. And so, bear with me now, I'm still practicing at this stuff, and sometimes it makes it a bit messy. And so called that RA, just let me, I can erase that, right? And that's from my motors course, where we're using RA. Okay, so RT is equal to, and I'm using the mouse to draw this out with, right? So it's a bit tedious. R1 plus R2 plus R3. Now normally I would include the units with each resistance value as I write it down, but just to make this a bit faster, I'm going to say that R1 has a value of 330. Of course we know that's 330 ohms, right? Plus R2, 110 ohms, plus R3, 200 ohms. And so that gives us RT is equal to, and we just take the linear sum of those things, and that gives us 640 ohms. Okay, so that's the first calculation. Now, we can, if we wish, put up here in our table, let's see if I can fit it in there, 640. Okay, so again, this stuff a lot of times is a bit tedious trying to do that with the mouse. So I don't know if that's any better. Okay, 640. Now, got 2 pieces of information about the circuit, right? And so that means we can apply Ohm's law to the totals. And so Ohm's law says that the current produced will be equal to the voltage applied divided by the opposition to the production of current. And if you remember that, you should always get Ohm's law correct. And so we have then 32 volts divided by 640 ohms. And so now IT is equal to 0.05 amps, And if you get used to writing that with your metric prefix, move your decimal 3 spots to the right and call that 50 milliamps. Now, I mean, you know, the reality of it is that you're going to want 0.05 for your calculator to do the rest of the calculations anyway, I guess, right? But that's the first part of the question. And so remember, concentrate on answering the question. So the current then, he's indicating here milliamps, right? So 50. Now, next we want the voltage drop across each resistor. Okay, so what we need to think about now is that from the rules of series circuits, we know that I1 is equal to I2 is equal to I3 is equal to the IT that we calculated. And so therefore, we know that the current here, 50 all the way through. And so once we realize that that current calculation gives us 2 pieces of information about each resistor, of course now we can apply Ohm's law to each resistor individually. And so therefore we should be able to say then that if I rearrange Ohm's law to solve for voltage, I have V1 is equal to I1 times R1, and that is 0.05 amps multiplied by 330 ohms. And so V1 is equal to 16.5 volts. Likewise then, V2 is equal to I2 times R2, and we have agreed that the current in each resistor is the same, and so again 0.05 amps times the resistance value of 110 ohms, and V2 then is equal to 5.5 volts. And so now apply Ohm's law to resistor 3. V3 is equal to 0.05 amps for I3 multiplied by R3 at 200 ohms, and V3 is equal to 10 volts even. Okay, so now we have V1, V2, V3, and so if I can put them in the table up here, 16.5, 5.5, and 10. And so we should verify that KVL holds true, right? And so one of the things then that we should do at the end, just check our work, is that we should say KVL tells us that we expect the sum V1 plus V2 plus V3 to equal the total applied voltage. And so if we do that, we have 16.5 volts plus 5.5 volts plus 10 volts, and if we add that up, we'll come up with, lo and behold, 32 volts. And of course, that is indeed equal to VT. So KVL verifies our calculation. And that means really that, we haven't made a mistake in there, right? Okay, so let's stop that recording now.